So I'll talk about multi-gigabit wireless multimedia communication and what are some of the technological changes. But in a nutshell, this talk is really about millimeter wave communication, because when you look at 60, 70 gigahertz, the wavelength and consequently the antenna size are of the order of millimeter, and hence the name. It's been known for decades in military communication, has been used in military communication. But recently, with the allocation of pretty well worldwide, something like 9 gigahertz in the 60 gigahertz bandwidth, and with the advances in process technology which allow you to implement them commercially, there has been a lot of interest in this. I have never prepared a PowerPoint slide in my life, so I should start off by acknowledging my doctoral student and doctoral student here at WINLAB, particularly Michelle. Jua Chan did some added slides on Mac and other things, and the person who introduced me to this topic is Professor Shudo Kato of the Hubei University in Japan. So I thought not many people know what University of British Columbia is, so I'll say a little bit about that. Then I'll say a little bit about society election, and then get into the talk by motivating a little bit about current standardization activities. There appears to be a lot happening. There's not only 802.0 series type standardization activity, but a lot of consortium led by various companies that are active in that. And after that, I decided to concentrate essentially on four core challenges. I list 5 there, though. So I'll just briefly touch upon them, namely the 60 gigahertz propagation and antennas, CMOS circuit design, the proposition being that if you are going to address the consumer market, you need to have a technology that is very cost effective, and CMOS seems to be the leading candidate, although the debate between CMOS versus Seagate is going to continue for a while, I suppose. Modulation schemes is a no-brainer because there's so much bandwidth available. You know, there's 9 gigahertz RF available, so and really they didn't argue too much about the choice of the modulation technique. There was one IEEE standard dealing with the UWB. I don't know how many of you remember that, and that fell apart because there were proponents of DSCDMA and proponents of OFDM, and the two could not agree, and the whole thing fell apart. So here you use the modulation technique that you like. Okay. And then LDPC codes for error correction. Just about all 802.11 series standards use LDPC codes. And I kind of scratch my head, why is that so? And there are not that many patents out there, so it's easy to incorporate a technology where a particular company doesn't hold a whole lot of patents, right? Then say a few things about net layer design. The talk has been collected from various sources, so I thought I'll share with you what we Hindus thought almost 4,000 years ago. Let noble thoughts come to us from all sides. And Rigveda was around 1700 BC. Is there anyone from Iran here? No one from Iran. So it turned out that in ancient Iran, before Iran became Muslim only in the year 1000 AD. Prior to that, they used to worship Zoroastrianism. And
this is the guy from Iran.
And the sacred book of Zoroastrianism is Avesta, and there are a lot of similarity within that book and the Rigveda. So in those days, there was a lot of traffic. You know, there was no visa requirement or anything like that. Nobody was enriching uranium or anything like that. So things are very easy. A lot of cross-cultural fertilization, and so on and so forth. When I have to consult my notes, I will go in Japanese mode and read some of my prepared notes. But anyway, so far so good. Okay. So this is a shot of University of British Columbia is it's a huge campus. It is the largest campus. You know, the whole university is in a single campus. You don't have to worry about going to, like Roy was telling me, he has to go to other campus and shell out $7 of parking or this and that. Here, everything is on this campus except to walk from one end to another is almost 15 minutes. Okay, so we try to schedule classrooms in a cluster of this. Those mountains you see beyond that is Whistler. That's where the Olympic Games were, Winter Olympic Games were held. That vast expanse of green you see in the middle of ocean is the Stanley Park. It's the largest park of its kind in an urban setting. And that's downtown Vancouver. You see that cluster. ICC 99 was there, BTC 2002 was there, and so on and so forth. A lot of conferences, very popular. And UBC has 48 square kilometers of forest. So you can see, which is non-contiguous, so you can see the forest all around. And we are the only university that has a nudist beach, which is right around here. Okay? No, seriously.
It's hard to tell it.
We have to.
Next one.
The university was 100 years old in 2008. We like to think it's a world-class university. There's a chair there. You know. It's a world-class university, we like to think, with a spectacular location. Highly ranked. Annual budget is about $1.6 billion. So I'm happy to say that the Canadian dollar is flirting with parity with American dollar, so it's almost 1.6 billion US. We are a large university. We serve about 45,000 students. And it's, in North American parlance, it's a comprehensive campus in the sense we have medicine, science, this and that. The world ranking depends heavily whether you have a Nobel laureate or not. So Professor Michael Smith was one of our own. He won the Nobel Prize in Chemistry. Unfortunately, he passed away in 2000. We got worried about our ranking, so we went south of the border and hired a Nobel laureate to move north. Okay, so the ranking is preserved. It's true. You know, the extent that, I mean, generally speaking, in Canada, we are not that rank conscious because we don't have private universities, so there are no Princeton or Harvard or anything like that. Every university is funded by the government. This is our department. This new building of our department, actually, we have 3 buildings, and it's actually, the photograph doesn't do justice to it. It has very striking white tiger stripes. So it's all glass in these stripes. So when you walk by, it looks, and our dean is proud to say, I don't know why, but this is the only academic building in campus that has a Starbucks in it. There are 4 Starbucks on the campus, but this is the only one.
I'm sorry.
Well, you know how, anyway, so 56 faculty members, you can read the statistics, and I belong to communication group, and there are about 7 of us. Some of these names you might recognize. I asked my student what if the names are in italics, and he said, oh, they are fellows of IEEE. So that's what it means. So these are our, pretty well, we cover the entire gamut of on wireless systems within the 7 of us here. My own current research is actually on cooperative communication, not on 60 gigahertz.
Hey, that's good.
That's good? You like cooperative?
Yes, I do.
Okay. So there's a commercial at the very end of this talk. I might as well tell you now, we're going to have a book out on cooperative communication from Cambridge University Press this fall. All right?
Nice.
And these are some of the topics that we are addressing. So with that, I'll go through this commercial very quickly. So as Michelle mentioned, I'm a candidate to be president of IEEE Communications Society elect. And generally when you run for political office, you say, oh, elect me, I will do this, this, and this. I'm going to take a reverse approach. I'm going to tell you what you did and what I did in my previous position. So I chair a committee for IEEE Communications Society. I don't know why this doesn't come through. It should say. So I chaired a committee that created IEEE Wireless Communication and Networking Conference. This week, it just finished actually yesterday in Sydney, Australia. And I was a member of a committee that created the IEEE Transaction on Wireless Communication. And of course, I was the principal organizer of ICC 99 in Vancouver. As president of IEEE Information Theory Society, my timing was impeccable. I was there in the year 2000 when we agreed with the city of Gaylord, Michigan, where Professor Claude Shannon grew up. And we said we would commission a statue and give it to the city if they dedicate a part after him. So if you go to Gaylord, Michigan, this is Shannon Park now, and you'll see this is a statue. And Professor Shannon is holding a piece of paper there, and there's a formula written there. So the exam question is to ask you at the end of the talk, what is that formula? Unfortunately, at that point in time, he was already advanced stage of Alzheimer. He was in hospital, so he couldn't come. So we flew his wife, Betty Shannon. And I still remember when we asked her that if he could know what's happening here, what would he think? And she chuckled when he said, well, he'd wonder what all this fuss is all about. Humble person, apparently. So anyway, that's the dedication, et cetera, et cetera. Okay. So let's get back to the topic of the talk. So the premise here is that in this band, you have contiguous spectrum available, and unlike the ISM band, where you're strictly limited by the amount of power that you can transmit, there's no limit in this band, the amount of power you can transmit. So if you contrast that with ultra-wideband system, which are an overlay system, and therefore not desirable in some sense, this one doesn't suffer from that. So vast amount of unlicensed bandwidth, and this might be debatable, but I think I would argue successfully that there is a mature CMOS design facility for low-cost 60 gigahertz devices. I'm not sure if anybody in the audience is in the gamut of implementing devices at such high frequencies, but so essentially then, you can talk about achieving data rates in wireless mode that almost approach wireline communication. So this is a state of affair around the globe pretty well. I couldn't find anything on China, but I assume that they too are talking about trying to come up with some kind of a ban. But as you can see that globally there's pretty well reasonable alignment. So this gives hope that there truly might be a global standard for WPAN in this band. But of course we have hope for global standards before, namely when we were talking about third generation and we eventually ended up with 3 different systems. So with this kind of frequency band, you can design consumer electronic product for all kind of application. You might have some kind of a kiosk, a sync and go. You can download all kind of information. You can have peer-to-peer communication. You can think of implementing gigabit wireless local area network, and all sorts of consumer devices are possible with data rate ranging from few tens to hundreds of megabit per second all the way to a couple of gigabit per second. So all of that can be possible with systems in this particular frequency band. And this is a cable taken from I assume it's a paper you're writing, Michelle. So she gave me this table, and there are a whole bunch of applications listed along with the kind of data rates. So essentially, the interest in this band is spurred by a large number of potential applications. So by the way, am I talking too fast? Do you understand my Indian English? No problem there? No. That's what happens when you come here and you're 18 years old and you don't speak much English. But I speak street English. So sometimes my friend had to tell me that Vijay, it's okay if you talk to us like that, but in polite company, we don't talk like that in English. All right. Standardization activity. So initially, until 2 days ago, my talk was primarily based on this, which is the IEEE 802.15.3c. It's started, I guess, 6-7 years ago, and the standard is almost complete. Primarily focused on file design, and but courtesy of Michelle and a colleague of mine, we were able to dig up several other activities going on. IEEE 802.11 A and D, largely driven by Intel, Broadcom, NEC. Wireless Gigabit Alliance, the proponents here, Intel, Broadcom, NEC, Apple, Dell, Microsoft, Panasonic, LG, Toshiba, etc. And as I said, the third one promoted mainly by a Japanese company, and then there's a European standardization, and then of course the wireless HD. So I was hoping to see Deepankar here, but I guess the director, he's busy. So I couldn't help but wave the flag here that there's a long history here which can be traced to an Indian scientist, Bengali scientist by the name J.C. Bose, Jagdish Chandra Bose, who in 1987 described to the Royal Society Institution in London the research that he was carrying out. Actually, this is not quite accurate. There was no granting agency, we were under British control, so he couldn't travel. So his mentor was Lord Raleigh. So he requested him to read out the paper, kind of. Sounds familiar, sometimes your supervisor doesn't send you to a conference. You have to ask some of your other people. He asked one of his friends to present it by proxy or something, right? So he used waveguides, horn antennas, dielectric lenses, polarizer, and semiconductor at that time, 1897. By the way, in the transatlantic experiment that Marconi conducted on 12 December 1901, which proved that the radio wave could indeed wave around, band, and transatlantic communication was possible, the diode detector he used was invented by him as well. So, but he was not even nominated for a Nobel Prize. We were under British there, and we were not supposed to be smart enough to be doing this kind of work.
For literature, it was okay.
Sorry?
For literature, it was okay to get Nobel Prize.
Yeah. So there are actually 3 Indians who should have got a Nobel Prize, but didn't. He's one of them. And there's another one by the same last name, Bose, but he was in 1949. Those of you who do quantum mechanics and other stuff, there's a Bose-Einstein statistics and Bose-Einstein condensates. That was a different Bose. He was hanging around 1945, and he should have also been nominated. But the biggest goof up was Mahatma Gandhi. He never won the Nobel Peace Prize. But anyway, enough about that. So the history goes all the way from 1897 to 1990, when FCC decided to open this band for commercial use. Okay.
So is Bose an Indian last name?
Yes. And he comes from the same part as your director.
So is it a frequent last name?
Frequent name?
Frequent last name?
Yeah, it's common.
Yes, it's common.
Yeah.
Because
Yeah, and people from Bengal are a little bit snobbish, you know, they think they're very smart. He's not within hearing range, right? You're Bengal? Yeah, so they have a saying that what Bengalis will think today, the rest of the country will think tomorrow. Oh well. I come from a backward province, the can I think of an American equivalent? Is there anybody from Wyoming? So think of me as coming from Wyoming of India. So it's kind of rural, backward, not much going on, that kind of place. You know, like Gansu, Qinghai, in China, Guizhou province, you know, those things. So you understand the kind of background that I come from. Okay, so here are some of the advantages of 60 gigahertz radio. As I said, you can have much higher transmit power compared to existing standards, where due to the requirement of low interference, there's a limit on the amount of power you can transmit. The signal is usually confined within a room due to high material absorption. I don't see why this is an advantage, but anyway. Higher throughput can be achieved through frequency reuse. And higher transmit power and the vast amount of bandwidth available allows you to use simpler modulation technique. And finally, because antennas are of the millimeter size, you can accommodate more antennas in a very small area. So these are, what are the challenges of these 60 gigahertz system? So I think this gentleman used to work for AT&T Lab, right? Harold P. Price. So one of his equations shows that free space path loss equation for equal antenna gain, okay, the path loss is proportional to the square of the carrier frequency. So that means the range of this kind of communication would be kind of limited. And essentially, it is limited to one room. It also suffers from deep shadowing, but that perhaps could be overcome by employing relays and repeater. Performance of CMOS circuit, while it is improving, it is still somewhat limited at high frequency. That's a challenge. And then baseband analog bottleneck, you know, how do you do processing at the receiver end at such high frequencies? You know, particularly when the interface circuits need to convert signal with very high resolution and operate at high frequency. So device complexity is likely to be very high. So with that as the background, I will now briefly touch upon the four issues that I identified. So in terms of propagation antennas, omnidirectional antennas that are used in some of the systems are inefficient because it is difficult to establish reliable communication, even in a line-of-sight communication at such high frequencies. For example, the human blockage can attenuate the signal dramatically, and therefore what you want to have at 60 gigahertz are switch beam antennae array or adaptive antennas, which may sound new to you now, but you know, it goes back to the work of Professor Bernard Wicker at Stanford in the early 60s. In fact, he wrote a book about it in the 60s. So you see some of these old things that are being done. So whatever fancy name you want to call it, by beamforming, antenna areas and all that, it all goes back to the work of Professor Bernard Woodrow at Stanford. So therefore, we focus on multi-antenna beamforming technique. Antenna array is very feasible at 60 gigahertz because of the millimeter wave size. You can stack them up. Antenna arrays could be used to generate narrow directional beam with high gain, thereby increasing the transmission range. And of course, it is well known that beamforming also reduces the multipath fading problem. Here are some other challenges might be our higher feed network loss, more complex phase network, stronger coupling between antennas and feed lines, etc. Also entering the challenge in the antenna design.
I have a question.
Yeah.
You said the beamforming will be with multipath. How is the multipath up to 60 gigahertz? Is it
I will ask my expert, Michelle, sitting next to you, to answer.
So there is multipath, so that's the question. There will be multipath from 60 gigahertz, but that multipath transmission is quite different from the Wi-Fi because in Wi-Fi we have rich scattering, so the use of omnidirectional is the advantages. But on 60 gigahertz, there is propagation is based on the line side and a few lines of reflection. So reflection, right? So the diffraction is very weak, and that totally fine.
Thank you.
Thank you, Michelle. I'll pay you later.
Okay.
Will you mention what sort of transmit powers have been achieved so far by whoever knows how to build these things?
So based on the 15cc, the GT3C standard, so that standard is for 60 gigahertz lifetime. That finished in last year, September 11. I think it should be 200 to 300 milliwatt.
So it's quite far.
Yeah.
The new one in 11AD will be approved in May. Because the draft from 11AD.
You might want to speak loudly so the rest of. Okay.
300 milliwatts, you said?
300 milliwatts, yeah. That's what I heard.
And does it work outdoors with the rain? There's
Oh, wow. Rain attenuation is another story. Foliage attenuation is another story. Not at those frequencies.
For the standard, there is no application scenario for outdoor, but academically, there are people studying outdoor mesh. So I think last week, Professor Matyas from UCSB, he came there for the interview, and he and his students studied the MAC 429 for 60 gigahertz in outdoor environments.
Okay.
So usually the antennas is installed on the roof for the building, but maybe I think those buildings have to be very close, and they have to maybe some kind of multi-home. So each of the transmission distance is still very short. Because
Do they go like 100 meters or 10 meters?
I didn't check their details, but they published a paper in this year's Ecole 2010. So maybe in that paper there's some data, but right now I cannot.
No, it's definitely not 100 meters. And I think it's fair to say that at the moment these things may not be possible, but people are trying to research ways and means around not only to extend the range, but deal with rain attenuation and foliage. But at the moment the answer is simple.
I think for one hole it's difficult to reach 100 meters, but maybe in multiple it's possible.
I think if I'm not wrong, the 11AD is
50.
11AD is 15.
I'm serious. Yeah, I think so.
50 gigahertz? 50 meters. It's supposed to be 60. Oh, same. Okay. Okay.
All right. So, you know, I mean, I'm an algebraic coding guy. What do I know about CMOS circuit design? But anyway, let me tell you. So historically, the cost of 60 gigahertz devices because I told you there are military system after all in this frequency. Implemented using compound semiconductor has been very expensive. So my definition of compound semiconductor is that these are exotic but not mainstream technologies and consequently expensive. Okay. Seagate versus CMOS debate will continue. And then I pose rhetorically the question, when will we see high-speed front ends with acceptable price? And when you do a little bit of search, you find that bulk CMOS process at 130 nanometer for 60 gigahertz RF building block has been demonstrated. Okay. What would really be nice is a fully integrated solution, CMOS solution, where you might have an analog front end and digital processing on what I call system on a chip kind of thing. That would be really nice. Now, we could claim that we have advanced to 65 nanometer, and as the size goes down, you know, the speed goes up. After all, the electrons have only that far to travel, right? No? Yes, Joe? Okay. The speed goes up, and potentially lower power consumption of the device. But there, you know, you don't, it's like the Rolling Stones song, you know, you can't always get what you want. So you gain some, you lose some, so there are trade-offs there in terms of gain. Experimentally, people have even demonstrated 35 nanometer CMOS. And if you ask if there is some kind of a Shannon limit on CMOS implementation, well, experts tell us that we may hit the wall around 20 to 10 nanometers. But it's still not nanotechnology, by the way. It still needs to go. There are two approaches to nano, right? You keep making things smaller and smaller, and when quantum mechanics starts to come into play, you declare it's nanotechnology. That's a top-down approach. The bottom-down approach is you put molecules at a time to construct your stuff. But the nice thing about CMOS technology is that it is driven by digital technology. So therefore, you can have analog front end and digital all in one. But for further improvement in CMOS circuit design, these are the challenges if any one of you is working in that area that I understand. Accurate device model capable of predicting the wideband performance of the transistor. Rigorous characterization and testing methodologies for predictable design. And optimized layout of CMOS transistor for maximum frequency of operation. Oh, time for another lighthearted. So many people from China here, right? So let me see if you can understand my Mandarin. So what this says, it says, San Ren Shin be your worship. Okay? Roughly translated, it means, and this is certainly true of me because I had the pleasure of visiting 72 countries so far and counting. It says that every individual has its own strength, and I can learn from them. And that's true. It's absolutely true. When you meet people, you always find something to learn. So who is this wise guy? In the English word, we call him Confucius. In China, they call him Confucius. Okay. He was born in a city called Chufu, which I haven't visited yet, but is on my list of things to do. Okay, well, modulation scheme, well, you want to be tolerant. I mean, you can use anything you want, but you want it to be tolerant to limited performance of CMOS circuit. And if you absolutely want to use OFDM, just make sure that you have low peak to average power ratio. Okay? Must be insensitive to phase noise. Spectral efficiency is not crucial. So you can use BPSK, QPSK, anything you like. I'm recommending MSK because it was invented in Canada. Okay, we called it fast MSK, but it shouldn't really MSK. Right? Is that okay? You buy that? MSK is a good candidate. It has constant envelope. It has a trellis structure. What more can you ask for? You know, constant envelope. You can pass it through a highly nonlinear amplifier and not worry about your AM to PM, PM to PM distortion. Nice. Okay, 60. Oh, by the way, how long is the seminar supposed to last?
About an hour.
Okay. Well, I have one of the occupational hazards of visiting many countries is that they're full of stories. You know, but you have come here to listen to 60 gigahertz, right? So I want to balance. So the idea here is that if you can do more analog pre-processing, then you will reduce the burden on the digital baseband processing. Now, the current buzzword, or the current name for that is digitally assisted analog signal processing, or mixed signal processing. It is this thing precisely that allows us to talk about system on a chip for these kind of scenarios. And then these are examples. What are things you can do in analog domain? Synchronization and equalization can be carried out partly in analog domain, and then simplifying the burden on the digital processing part. It allows you to simplify requirement on analog to digital converters. Synchronization and equalization parameter errors can be estimated in digital domain and corrected in analog domain. So that's all I want to say about that. Low density parity check, folks. So as I said in the beginning of the talk, all the 802 standard series and also the European standard, they have all adopted low density parity check codes. They were actually invented by Professor Roy Yates' supervisor, and then people promptly forgot about it. And then some British guy reinvented the wheel, and he said, oh, rediscovery of Gallagher's low density parity check codes. Anyway, so they were, why are they called low density parity check codes? Because literally, when you look at the parity check matrix, it has a small number of ones, and hence the name low density parity check code. So the major challenge for 60 gigahertz, to state the obvious, is to design low complexity and high throughput decoders. Rate compatibility is important because I showed you that table that Michelle gave me, which has 14 applications with different kind of data rates, so different kind of codes will be required. So you want the same decoder to be able to decode codes at different rates. That's the idea behind rate compatible codes. And to achieve a good trade-off between complexity and performance, it is of interest to explore LDPC codes based on circulant matrices. These are matrices which are completely characterized by their first row. These are n by n matrices. You characterize the first row, and all other rows are cyclic shift of the first row. Okay. And also using combinatorial optimization technique. So just to show you, this also tells you the rate compatibility. So this is the parity check matrix of a rate 1/2 code 5676-288. Now we obviously cannot have a matrix that will have 288 columns and rows and 576 columns. So this is a short way of representing them. And the sub-matrices are circulant matrices. And what I mean by rate compatible is that the parity check matrix of rate 1/2, 3/4, and rate 7/8, they're all related, and you know, the decoder will be able to work for all these three. So to go from here to this 3/4 code, you simply slice off the bottom 8, how many rows? Bottom 8, okay? But so it's the parity check matrix from which you have clipped off the bottom 8 rows. And you can go to 7/8 by clipping off this one. So LDPC code are also readily amenable to rate compatibility. And on this transparency, bright PhD students from WINLAB have generated performance curves for codes used in various standards. You know, there's codes that have been implemented by Broadcom, by Intel, in the IEEE standard. And the conclusion about the good code design is that it must have low decoding SNR. So, you know, if you're interested in voice only, 10 to minus 3, you're talking about only 2 dB, right? And 10 to minus 7 also 3 dB. So it's pretty good. Okay. You also want to have low error floor. You don't want your curve to go already like this. You want to go further down before it floors. And even then, of course, techniques exist to get rid of the error floor, right? You can always concatenate it with a read-sound encoding, get rid of the error floor altogether or lower it further. So lots of tricks. And of course, goes without saying, low complexity. Bank protocol. So of all the 4 topics, I know the least about it, but let me consult my notes in that case, since I know the least about it. So first observation is that 60 gigahertz WLAN favors directive communication, because due to high attenuation through obstruction, a communication link in 60 gigahertz is more vulnerable than, say, with Wi-Fi counterpart. However, conventional WLAN are designed for omnidirectional antenna, whereas for this you need directional MAC. But sorry, I think it's better, Michelle, if I ask you guys. You want to come over here? Oh, you want to come here? Feel free to use this PowerPoint. You prepared them, right?
Oh, yeah. So you know that, so nowadays we use 802.11. It's using omnidirectional antenna. But as we talk about 60 gigahertz, we have to use beamforming and use the directional antenna to get the higher gain. Right? Otherwise, if we use omnidirectional antennas, we can only transmit 2 or 3 meters. The range is very low. So we have to use the directional antennas. But directional antennas is inherently incompatible with CSMA. We know that the 802.11 network, we use the CSMA as the media access protocols. But directional antennas, well, incompatible with this. Later, we following 2 slides will talk about 2 problems. One is called deafness, and another is called directional hidden terminal problem. So we have to change the MAC protocol to accommodate to the 60 gigahertz. So also there are another property of the 60 gigahertz is high propagation loss, which we have talked about before, is we can use directional antennas to solve this problem. But another problem is the blockage. So because the 60 gigahertz, the frequency is too high, even if people is standing in front of the antennas, it will block the transmission. So do not let the 2.4 gigahertz. It can avoid the people, and you can also receive it. So to solve the blockage, we can use such methods such as multipass. We can use some direct antennas and make a reflection to avoid the blockage. And also we should use MIMO, so a number of antennas to do the beamforming and to do the directional antenna. And this is the problems of the deafness. So for example, if no device A want to talk with device B, it will make some directional antenna point to the device B. And also device B will make a directional antenna to beamform to talk about device A. But if another device X, if it wants to talk to device A, but device A is beamform his antenna to device B, so he's deaf now, so he cannot it cannot receive the packet. But device X do not know such thing that device A is deaf. Then he will retransmit the RTS or transmit data packet. There maybe waste a lot of energy. And also in some cases that if device X send a lot of packet and do not receive any acknowledgement from device A, so he may think that device A is lost. So he may propose a new, develop the new routing table that is also not efficient. Another problem is called directional hidden terminals. So all of us may know that wireless LAN we have the problem with the hidden terminal. So if we introduce a directional map, so this problem will come again. For example, if device A and device B is communication with each other, and another property of the beamforming is that the transmission range may be different in each direction. Maybe in these directions, the transmission is longer, but in another directions, the transmission range is maybe a little lower. So that will cause the problem. If the device B wants to send a packet to device C, but its transmission range is a little longer, so it will accidentally cover the range of device A. So the device A maybe receives the packet from device B and device C at the same time. So it will cause circulations. So we have to consider all of these ratios when we want to use the 60 gigahertz into the wireless local network. So that is maybe the group 80 is now doing this.
Okay, so it seems that it is not interference sensitive at all, like it is range limited. Yes.
Yeah, it has range
Okay.
limit.
So in the 11AD, they are discussing they want to do MU-MIMO, whole user MIMO for transmission in the outplane.
Yeah.
Why would you need that if you don't hear each other from the start?
So
Why do you see the problem with it?
I think it's just the option. So we're doing that more beyond the standard. So consider more general topic and try to come up with a solution. So we're not exactly following AD.
When you speak of directional beams,
yeah.
should I be thinking, I'm not really sure what people are just talking about at high level, what people actually building or designing or already did. But should I be thinking phased arrays, or should I be thinking little horn antennas that work at millimeter frequencies? Is there a discussion on that, or someone else does that?
Yeah, I think AD, I'm not sure what's the definition about because sometimes the framework that on the ground is not being disclosed publicly. But to my understanding about TG3C, the past wireless pipe standard 6 meters, they're not doing beamforming on the physical layer. They're doing beamforming on the net layer. they sort of, they do not need the information about the angle level, the channel level. They just use some code to do the beamforming.
But eventually they have to shoot the right way, so.
Right, they do some mechanical like scanning, and then identify the. Yeah, actually, it's difficult to say explain in a few sentences. There's a paper published in design.
Do they use one antenna or multiple?
They usually use multiple.
Multiple antennas, a fixed number of antennas, but they do some energy detection by scanning.
In theory, not a big theory.
Yeah. So we call that information actually. The line technology used to define the Wi-Fi.
Okay, so amongst the two choices, I could imagine one choice is having a bunch of forms kind of looking out, and you switch around and look where you may be receiving things.
Yeah.
Or the alternative is you can have elemental antennas, and as the phrase goes, you read the phase route. It's the second one, or the horn. That would be more reliable.
So, but it's still, in either context, I don't understand directional deference. Because in the one context, the phased array, right, you could combine the signals, the arriving signals in some other way to extract this other signal that you showed going from a different direction.
The way multiple receiver.
And if you have multiple horns, then there's each horn has a pretty good signal, either this way or that way.
You just pick the big
Or each one carries, and can acquire a signal, a strong one. So it seems like this directional deafness is just kind of a constraint derived from a receiver that just doesn't know how to process more than one signal.
Or maybe it's a money-saving technique, like you only have a single receive chain.
Yeah.
So you just, at any one time, you can only listen in each direction.
Yeah.
Maybe that's the money thing.
Yeah, which is not a, I guess, I'm not sure if money things are technology.
Well, it might be a technology thing in the sense that it's hard to process. They have hard time processing a single chain.
Yeah, okay, so that supports his.
Oh, okay. And did people, besides conversations and standards, did people build a primitive one that kind of works?
Yeah, we have some protocol about how to be formed.
No, but did somebody build things that actually really work?
I think in Japan, they have a national lab called NTT, so they are the major promoter for the TD3C, the 60 GHz wireless band standard. So when we visited their group, I think Vijay was with us, they're supposed to show us the demo, how the 60 GHz, the beamforming antennas work. But it doesn't work that day, so.
Oh, okay.
I hope it's ready now.
Vijay mentioned the military applications. I guess I'm just wondering, I thought military goes for big things, long range, reliable, and I'm curious, what they did with 60 GHz? Or did they just grab the spectrum and kept it for a while?
No, there are systems that as I said, not that deep into it, so I don't really know. That's the honest answer. Yes, your other statement is cute. Yes, military all over the world is notorious for grabbing a lot of spectrum and not doing anything about it. We have a huge problem in India. They don't want to release it, and it's a huge problem. And from your remark, I gather there seems to be a problem in other countries as well.
I have no idea, but that's my guess.
Oh yeah, that's very true. They grab the spectrum. Okay, so more on Mac design. There are 3 handover integration which take place at link layer, and that one is more or less some kind of a software adjustment. Upper MAC integration, which is designed for upper MAC functions such as association, security, and channel time allocation, more software changes, and full MAC integration, which is kind of hard, require both software and hardware changes. So to conclude, and I'm delighted that audience is quite a bit knowledgeable about it, the commercial success of 60 gigahertz WPAN, WLAN device will depend on design of efficient multi-antenna beamforming technique to combat heavy path losses and penetration losses of 60 gigahertz. Design of low-cost and low-power CMOS circuits that operate efficiently at 60 gigahertz. And there's hope there. Design a suitable modulation scheme that take into consideration restrictions imposed by CMOS circuit. Quite a bit of progress made already on development of high throughput and low complexity decoder architecture for LDPC codes. And there's actually a paper in IEEE Communication magazine last month that talks about high throughput LDPC decoder, but in the context of fiber optical communication. But a lot of progress being made in that area. And design of a suitable direction map, MAC. So I'll end it with a final, these are some references on which this particular talk is used concept from some of these papers. And finally, another commercial. There's a book coming. It's an edited book. It's on the cooperative cellular wireless networks. Edited by Professor Ikram Singh from the University of Manitoba in Canada. Dong-In Kim from Sinkin Kwan University, which is a unusual university in the sense that Samsung purchased the whole university. So everything is paid for by Samsung. And also students are carefully selected when they graduate from this university. They go and work for Samsung. Dong-In Kim was a student of Bob Schultz and his academic brother of Mo Lin. They were both together students of Bob Schultz at the University of Southern California. And myself, if you are interested in some of the topics, I won't bother reading all the time. These overheads are readily available to you unless WINLAB copyrights them.
Green communication. What is green communication?
Green communication?
Of course.
It's green, like this bill. Like this American dollar. It's green. No, it's essentially to do with power saving, in the serious way. Okay? So you could do simple things like you could turn off base stations in the evening when the capacity and coverage requirements are minimal. And you could focus all your designs from the concept of saving power. Because, well, I was told that all these billions and now approaching trillions of wireless devices around the world consume 4% of world's energy. It's hard to believe that, right? Because we think that our BlackBerry runs simply by sniffing current. You know, how much power is going to consume. But when you aggregate these trillions of devices, that's why it works out. So it's a huge carbon footprint, and therefore you want to minimize that. So you got to design your systems with energy efficiency in mind. That's actually from Gerhard Febleis's book, this particular chapter. Okay? And a few more LTE and this and that. So this will come out in the fall from Cambridge University Press. So I would like to thank yourself and Michelle. And as a token of my appreciation, I'd like to present her with this book, which I edited with Nuspl and Tarokh and Yoon. Thank you very much.
Okay, thank you.